Okay, this is a review for the test coming up. Just a couple things you need to know. You're going to have 10 either true, false, or multiple guess questions. They're going to address things like the relationship between the horizontal and the vertical velocity, how to calculate that if you're given the initial velocity and the angle, the direction of centripetal acceleration and centripetal force on an object that's in uniform circular motion. You need to be able to calculate centripetal acceleration and centripetal force. And you need to remember what the definition of a trajectory is and a projectile and how that plays into the chapter. So let's also then look at the four questions you're going to have. You're going to have four questions similar to the following. The first one, let's say we have a football that's kicked off of a tee, 12 meters per second at an angle of 72 degrees above the horizon. We want to know the maximum height the football gets to and how far does it go. Well, the first thing we want to do is we want to break up our velocity into the initial velocity of 12 meters per second into its vertical component and into its horizontal component. And of course we do that using a little bit of trigonometry. We know that the vertical component, essentially this green vector, can be over here. So this would be the opposite over the hypotenuse is the sine. We could figure out the vertical velocity is 11.4 meters per second. The blue one down here is the adjacent over the hypotenuse, which is a cosine. So that gives us 3.7 meters per second. Once we know that, we're going to work on, first of all, the vertical velocity. In other words, how fast it goes up, how fast it comes down, and then this area right underneath here will give us the maximum height. So if we know we start out at 11.4 meters per second and the only force acting on it is acceleration due to the force of gravity, 9.8 meters per second squared, we could figure out T1 is when it's at its peak. T2 is when it hits the ground again. We're going to first of all figure out T1 by doing the slope, which is rise over run, gives us 1.66 seconds for the time. If we want to figure out the maximum height, 1/2 base times height gives us a height inside this area here of 6.6 meters. Again, we want to know how far it gets when it travels the whole distance, so now we need T2, which is when it hits the ground again. So we're going to use this square graph down here. We figured out earlier that the vertical velocity, or excuse me, the horizontal velocity was 3.7 meters per second. It did that for 2.33 meters. Multiply base times height, and we get 8.6 meters. Okay, let's take a look at another one. We're swinging a stone on a sling, so the barbarian swinging a stone, the sling is 60 centimeters long. Remember, we'll have to convert that to meters. The period it takes to go around is about 1/4 of a second, so he's swinging around pretty fast, four swings per second. So at about 0.23 seconds, and the centripetal force is 34.7 newtons, and we want to know how heavy is the stone that he's swinging if all this is true. Well, first of all, we could figure out the velocity if we know the radius and we know the period. 2 pi radius over time is going to give us 24.6 meters per second. Once we have that, we could figure out the acceleration, take the velocity squared over radius, and that gives us 671 meters per second squared. I would strongly suggest you actually do some of the stuff on your calculator, make sure that I'm getting the right answers, and make sure you see how those answers are derived. If you're just sitting here watching this while you're talking on your phone, you're probably not going to get a whole lot out of this. Anyway, so we got the velocity, we got the acceleration. Remember, force is equal to mass times acceleration. Well, I gave you the force, and we calculated the acceleration. We can then derive the mass, basically taking the force divided by the acceleration, and we get a stone that weighs about 50 grams, about 0.052 kilograms. Let's go on to look at some children playing on one of those merry-go-rounds. Each kid weighs about 30 kilograms, which is a little over 60-something pounds. about 66 pounds each. They're riding around. You got one kid closer to the center on the edge of the platform, the other one's on the outside edge of the platform. And the platform on this merry-go-round is 5 meters wide, and the whole merry-go-round is, the diameter is 21 meters from one edge to the other. So we're going to be looking at, in this case, the inside rider. Again, the rider weighs 50 kilograms. If the whole platform is 20 meters across, then the radius of the merry-go-round is 10 meters. And if the platform itself is 5 meters wide, if the outside is at 10 meters, then the inside of the platform has to be at 5 meters. So we get a radius of 5 meters. Each kid still takes 90 seconds to go around. That doesn't change. Once again, we could figure out the velocity, 2 pi r over t, and we get 0.35 meters per second, kind of just slowly going around. We can take that velocity and we could calculate the acceleration, and the acceleration towards the center is 0.24 meters per second squared. And now we're going to do force is equal to mass times acceleration. This time I gave you the mass, we calculated the acceleration, and we're going to go back and figure out the force at 0.73 newtons. Finally, we have a bolt shot from a crossbow. We're holding the crossbow at 1.5 meters above the ground. And we want to figure out the initial velocity if it's traveling at if it travels 25 meters before it hits the ground. So this time I gave you the height off the ground, I gave you the distance that it's going to travel. Well, if we could figure out how long it stays in the air, then it's easy to figure out how fast it's going based on how far it went in that time frame. So we need to figure out how long it's in the air. It starts at an initial velocity, downward velocity of 0, and it accelerates towards the ground at 9.8 meters per second squared. Doesn't matter whether it's flying through the air or dropping straight down, that holds true. And we know that it fell a total of 1.5 meters, so that's going to be the area of our triangle. So we know that slope is rise over run. We know that the area of the triangle is 1/2 base times height. So we can take the t here and put it over here. And so velocity is going to be 9.8 t. We're going to substitute that in for velocity down here. So now we have the area, which is 1.5, is equal to 1/2 of t times 9.8 t. T times t is t squared. And if we take 1.5, we're going to multiply it by 2, get 3, and then we're going to divide it by 9.8, and we end up with 0.306 is the time squared. That would actually be s squared if you wanted a measurement. And we're going to calculate that out to be, oh, come on, is it going to let me do it? No, where am I at? Let's go back. Okay, anyways. That ends up being 0.553 seconds. So it takes about 1/2 a second for it to hit the ground. It's going to go 25 meters, so how fast does it have to be going if it hits the ground 25 meters away? Now we're back into this equation, but again, we're working backwards. We have the area. We have the time that we just figured out, how long it's in the air. Now we want to figure out the velocity, and the velocity is 45 meters per second, basically base times height. So we're going to take 25 and we're going to divide it by 0.553 seconds, and we get 45 meters per second squared. Okay, so that's it.